in these circles need no introduction whatsoever, but on the odd chance that no one's encountered me before, this is Daryl Home from Imperial College, formerly and probably still of Los Alamos as well.
No, they fired me.
They fired me, well done. And so he's going to talk about parameterization, the thing that everybody said they wished someone would talk about.
Yes, we just had a discussion, a breakout discussion about what we're going to do in this program. So I wanted to just add my part to what Hillary was writing. So I'm interested in multiscale models, the interactions of disparate scales. So I'm your entertainment for this afternoon. And my approach in this problem is to enforce, enforce selective decay of the Casimir's constants of motion of the ideal fluids relative to, or the energy. But what we talk about now will be decay of things like entropy relative to energy. And I'll explain why we start out with that. Although it could be decay of something else with respect to that, any kind of pair you want to choose. There is a general theory for the selective decay. I'm going to sketch it out for you, talking about the Lie-Poisson structure of the ideal fluid theory in 2D and 3D, just generally, and then give some examples. And it turns out that these examples can make some relationship between selective decay by Casimir dissipation and a method of anticipated vorticity. Okay, so anticipated vorticity, I first heard about this from Jack Herring. And he made the point that this model, regardless of how well it works, it has this sort of interesting feature to it that he couldn't put his finger on at the time, and I was working on a different kind of model at the time, and I couldn't put my finger on it either, but I think now I've got some better idea for it. So I'll talk about incompressible turbulence in the selective decay that's seen there, and get to the problem statement with verbs, and use this approach of Casimir dissipation. Casimirs are a property of the Poisson bracket in that these are the functions that commute, Poisson commute with any choice of the Hamiltonian. And that you'll see why this is important when we start talking about the general theory. So it turns out there's this connection of the Casimir dissipation to the 2D anticipated vorticity scheme, and it's associated with a lot of considerations that people have done before. I'll review those, and then talk about generalizing the idea of anticipated vorticity to 3D Euler fluid equations, and then just give a couple of examples in 2D and 3D, including the basic model for ocean circulation. Okay, ask questions as we go, please. Okay, so in 2D turbulence, this is a simulation. As Jim McWilliams says, right, the vortex patches of each sign merge to become larger and sparser, and the filaments stretch into jets between them. In 3D, things are quite different. There, the 3D stretching decreases the diameter of the vortex tubes and makes things actually just frighteningly interesting. This is a 2,000 cubed simulation that was done at Los Alamos by Mark Taylor. This is 2,000 by 2,000 and a 128 slice here which just happened to catch that vortex tube right there, whose vorticity on the exterior is whatever that number is. But if you look in the interior, these vortices are spinning faster. Okay. The other point about this run at this high resolution that shocked me is I thought we would see the same tubes at 2,000 cubed that we saw at 500 cubed, but just like more of them in more detail. But the balance, it works out that the higher your resolution, the smaller those tubes. There are nothing like this. The 512 cubes tubes are not here at all. It's a completely different game. It's a different balance. Okay, well, 3D is where we like to go to keep this sort of thing in mind. This is incompressible. If we go to 3D compressible, then acoustic waves radically change the structures, and I'm not going there now. This is a very complicated problem. And this is an illustration. This is analyzed data coming from ECMWF of 3D motion on a preserved 2D level set. It's a snapshot of the northern hemisphere, showing the contours of potential temperature on a level set, which is essentially the tropopause, a level set of the potential vorticity. And it shows all kinds of 2D stretching. 2D stretching is what these 2D incompressible turbulence problems can do. They merge, the large-scale structures grow, the small-scale structures dissipate by viscosity. Okay, so one of the basic building blocks for this theory is going to be the ideal fluid conservation laws. Okay, so we get those from the Hamiltonian description of Euler's fluid equations using a bracket called the Lee-Poisson bracket. So I suppose, like David says, everyone in this room knows that Euler's equations are Hamiltonian in the Eulerian description. In 2D, if you think about, I'm going to define this bracket here, now which has three things in it, F, H, and C. They're functions of the 2D scalar vorticity omega, and I'm calling this thing a Nambu bracket. Other people call that too. It turns out this is the key to making the generalization. If this guy C is the Casimir, if you choose the Casimir to be the entropy, the bracket is the Jacobian bracket. If you choose the Casimir to be the entropy, then dc d omega is linear in omega, and we get that. This then yields the Lee-Poisson bracket. I guess people know about, but in particular, if we now let F be omega and put it into this machine with this bracket, then we get the Jacobian bracket of dc d omega with the h d omega. And when the Hamiltonian is the kinetic energy, the h d omega is the stream function, and this gives the Jacobian bracket of psi and of omega in the stream function, which is minus u dot grad omega, and omega is carried around by the flow of u. Okay. So here's the first theorem to define the Casimirs. So it turns out that there are two kinds of conservation laws for the 2D Euler problem. The first one is the energy, and it's conserved because the Poisson bracket is asymmetric, and it's in the Poisson bracket that the motion gets generated, just like we saw. And also the Casimirs, which in this case are integral of any function, any smooth or continuous function of the vorticity. It satisfies its time derivative. This variational derivative gives us a phi prime. This Jacobian bracket has the property that it rotates like this and gives 0 for all h. That's a Casimir. This is what we mean by a Casimir. The Poisson bracket commutes with all the Hamiltonians. See, this one here is conserved. And this is why there are two kinds. The energy defines the dynamics. The Casimirs are conserved just by the geometry of the problem, by the Poisson bracket for the problem. Okay, so let me say a little bit about inverse cascade and selective decay. Since Fjordhoff, we knew that this quadratic inviscid invariants globally constrain 2D turbulent flows and strongly affect their energy cascade. Fjordhoff already said that just looking at the conservation of both energy and entropy would imply that for any transfer of kinetic energy to higher wave numbers, it must be accompanied by a larger transfer of energy to lower wave numbers. So energy tends to go to lower wave numbers. Quakenon, in the late 60s, used some thermodynamic and statistical physics arguments to predict the scaling of the forward cascade of entropy. So this is the Casimir dissipating, and the inverse cascade of the kinetic energy for 2D turbulence. And a good review is Quakenon and Montgomery. Around 1980, Mateus and Montgomery performed these numerical simulations which bore out the expectations from the Quakenon theory as well as they could at the time, and introduced this term, minimum entropy or selective decay. Selective decay is the term we'll use, okay, for the decrease in a constant motion of the ideal theory due to the presence of nonlinearity and dissipation in the viscous theory. Okay, so we know we have these two types of conservation laws, and that they're both properties of this Lie-Poisson bracket. Well, we know they have different dissipation rates, and we see this as a large effect on the properties of the viscous flow, namely its characteristic inverse cascade. And the two types, this is one of the things, you compare the energy and the entropy and say, what's the difference between them as quantities? Well, one of the main differences is that they depend differently on the spatial gradients of the solution. They're both norms. One is the L2 norm, the other is the H1 norm, and it measures the second one measures the higher wave numbers. So in some sense, this balance and the interplay between in this decay is some kind of interaction between larger and smaller scales. Okay, and if now we have the control, if we can impose a selective decay on one or the other, then we can enhance one set of scales over another set. We know what 2D incompressible turbulence does. 3D incompressible turbulence doesn't do the same thing. So we may need to have some kind of flexibility. And we'll have the flexibility by producing a general theory. In the case for the decay of entropy at constant kinetic energy, the gradients in H1 decrease, magnitude in L2 stays the same, and basically the solution gets smoother, get larger structures. Right, that's the inverse cascade. Okay, so Mateus and Montgomery postulated this inverse cascade as a determining principle for 2D turbulence. So here's our problem statement and the approach. And so the question is, now that we know all this about the ideal flow, and we know that these two ideally conserved quantities are interacting with each other in the real problem, the viscous problem, could we use the Lie-Poisson bracket to impose the process of selective decay that we're interested in. Okay, so can we use it in particular to modify the 2D flow equations so that those equations with the absence of viscosity produce the selective decay, so that some kind of nonlinear viscosity is coming into play, if you're thinking about this that way. The other feature about that, setting up this cascade and the inverse cascade with viscosity, is that it takes a pretty long time for it to actually get, settle down. But maybe we could do this with only one time scale and just have the solution emerge from these modified 2D flow equations. Okay, so here's our proposition. We're going to use two brackets. We use the one we had. It's the Nambu or Lee-Poisson. I'll explain why it's Nambu in a second, which is bilinear, antisymmetric, acts like a derivative on products of functionals, and satisfies the Jacobi identity. And now we want to introduce another bracket. This is the dissipative bracket. It would be bilinear but symmetric, like a metric, and act as the derivative and be positive semi-definite. If it were positive definite, we could think of it putting a Riemannian metric on our space. But we can allow this thing to go to 0. And 3, together the two brackets should satisfy that the Casimirs commute with any Hamiltonian, and that the symmetric bracket also vanishes when you pair H with C. And these other properties should come in the definition. The Lee-Poisson bracket should be antisymmetric, and the dissipative bracket should be symmetric. So now if we use a linear combination of these brackets for the dynamics, F is the antisymmetric bracket with H, the symmetric bracket with C, and theta is some number which will start out being positive. This will yield the selective decay if we first choose F to be H. If F to be is H, then let's see another example. If F is H, then that guy vanishes, and this guy vanishes by that assumption. So dH dt is 0. If F is C, well, C commutes with everybody, so that term vanishes. And that term is greater than or equal to 0, so multiplying it by minus theta makes something less than or equal to 0. So dC dt will decay until it comes to some stationary point. Okay, this is the structure. This structure, well, the question is, can we do that? And here's an example we can do it. If we just think about vectors with cross products of gradients of functions, this one here, our antisymmetric bracket is in this form called the Nambu form in R3 for gradients of smooth functions. And our other guy is even with some pairing like a metric between the cross products of C and H and the cross products of F and H. Okay, so these equations, if we now put in H for F, will give us dH dt equals 0. And dC dt, right, we put in here C for F, and dC dt is minus a square. And if we're asking what does the motion do, then we put in for F dx, just the spatial variable. It gives the first part, which is the cross product, which is actually the same cross product you see in rigid body motion. And then the second part now we can think of as some kind of torque that was introduced into the dynamics by requiring the selective decay. It turns out that the structure of this little example takes us straight into fluid dynamics when we put in the Nambu bracket for fluids and the Jacobian bracket for that cross product. Remember this cross product here. Okay, so if we put that in, that's the natural candidate. Choose C, for example, a quadratic C. The sign of theta is going to matter, and I'll come back to it later. And we're going to add one more thing, because remember the selective decay has something to do with scales. Okay, so we could introduce a differential operator here, which would give us some sense of scale awareness in the Casimir dissipation. So it might, for example, it might only turn the Casimir dissipation on when the wave number is sufficiently high. Okay. So those two brackets satisfy the properties that we wanted them to have. They now govern the dynamics in a simple way, and they produce energy conservation and Casimir decay. So this is our candidate for selective decay by this Casimir dissipation. Now, there is a connection you might want to make, is that if theta is 0, then we're back to the Hamiltonian case. For theta is greater than 0, that's our selective decay case. But for theta less than 0, then there's another whole branch of investigations of this kind in which you think of the Casimir as some kind of entropy. And you think of this as the first law of thermodynamics, and that's the second law of thermodynamics. And this whole idea of adding a symmetric part to a antisymmetric motion is reflected in a lot of places in mathematics. If you add a metric to a symplectic space, it's called a Kähler space, provided you have that compatibility condition. And if you look up investigation, Kähler spaces, it's a big activity in mathematics. Yeah.
Darryl, I'm used to if you have some dissipative term and then you flip the sign, the equations would be ill-posed or something.
Yeah, you might be right. I thought about that too, but we would choose. Let me say a little bit about that. Okay, I thought about that, but if, for example, if you took, if you were looking at the Vlasov equation, okay, and your quantity that was evolving was the probability distribution in phase space, then you would have the opportunity to use the entropy as this other Casimir, right? But it may turn out you have to change the sign of the entropy. I don't know. Could be you need the H theorem. But I want to say that now because later on this connects to what went before. Okay. So also this is a way out of the case with helicity. It turns out you could, if the Casimir is not sign definite like the helicity, then its square is still a Casimir, and then you can use it instead. Okay, in the sense, so it's a nice little trick. Okay, so here's the connection to 2D anticipated vorticity. So we put f of omega is omega into our equation. Here is the antisymmetric part and the symmetric part. And now it's appearing as a double bracket. And for fluids, dH d omega is the stream function, and dc d omega, the entropy, is omega. And so this gives us this psi with omega like we had before, plus theta psi with L on psi on omega. And when we write that out, in terms of bracket of psi with omega being u dot grad omega, we get the anticipated vorticity equations. Okay, and these equations can be written equivalently by defining a modified or anticipated vorticity, right? This is well known, but it turns out that this structure can, with the modified vorticity, you keep the same form of the equations, but you modify the vorticity that are being acted on. It goes off into 3D, it goes into stratified, rotating. It does potential vorticity, of course. So it'll do shallow water. Everything will always appear in this form. So you'll have a familiar equation, okay? The same form you always use for your vorticity, but the new vorticity, omega twiddle, will involve this double bracket, or this bracket, which makes it into a double bracket. You know, and it can be thought of as an anticipation. Yeah. Okay, so these are the equations that we were just talking about, comprises anticipated vorticity scheme. And this scheme has been being developed now by Chin, Gunzberger, and Ringler. And using L as the choice of the scale selection operator and developing numerical algorithms which have this property of being scale aware. Okay. And here's a remark. If we look back at this equation here, you see psi with omega again. So the equilibria of the original problem are also equilibria of the modified problem. And the decay of the question is, you know, it's probably certainly true. It's certainly true in examples that I've looked at, is that it seems that this decay of the Casimir just takes us back to equilibria of the original problem. Okay. So, precedence, a little bit of history. If the operator L is just the identity, like I mentioned, you have this double bracket dissipative structure, and that's been studied quite a bit, but it differs from recent studies by Block et al., and in which I've been involved, by switching H and C. Switching H and C, though, we know that that does the other thing, right? Now you'll be dissipating energy and holding the Casimir fixed. So there is this duality already that appears in some applications. And considerably earlier, Alan Kaufman and Phil Morrison both proposed what Phil calls a metaplectic approach, in which he introduced a symmetric bracket, and an anti-symmetric bracket in this form, and looked at the properties that the G must have in order to satisfy what I said were the desired properties, which now this is this idea of the first and second laws of thermodynamics. So the history is that these guys developed with that thermodynamic purpose in mind. Okay. Also, more thermodynamics. Miroslav Gromela and his collaborators have pioneered a method that's called generic for modeling thermodynamic processes and dynamic, non-equilibrium thermodynamic processes in continuum mechanics. So there's a lot of activity in this direction already. Okay, and earlier, VCY, Vallis, Carnevale, and Young proposed a different modification, which modified the transport velocity, not the thing that u dot grad acts on, but u, which would dissipate energy, but with fixed Casimirs. Okay, so from our viewpoint now, we first know that we would switch H and C, but then it turns out that in this metric term, there's a completely different mathematical structure than in the VCY 89 paper than in the anticipated vorticity work. So it's a dual thing. Now you could think about, yeah, okay, so we're interested in this kind of modification. What about the dual modification? Is that good too? So we can think about that. But they're essentially different. On the other hand, and one of the ways in which they're essentially different is this VCY 89 equations actually conserve the momentum. They have a circulation theorem. Yeah, Yeah. So, and this stuff here with the different mathematical structure arose in a paper that I did with Vakang Putkaradze and Chetri Tranchi. But if you want to see how this all works together in the fluid situation, look at the VCY 89 and the JFM.
So AV doesn't have a circulation theorem?
No. Well, it has one, but it doesn't conserve circulation. Okay, because I'll show you in a second that there's the right-hand side.
But the right-hand side is a flux of vorticity.
We'll come to that. Okay, so this works perfectly well for potential vorticity. It's just a minor modification of adding a linear term to the stream function. And that gives us anticipated potential vorticity equation. And you see it's the same structure, but you just change the thing that's been that was being acted on before by the transport velocity. Okay, so let me get now to start to 3D. So in 3D, we have this for the Lie-Poisson bracket, and in the equation that comes out by using this procedure is the omega dt is the curl of dh d omega crossed into omega twiddle, and this is the modification of omega in 3D to dissipate the Casimir. And of course, it reduces to anticipated vorticity in 2D. And if we look at the fluid case itself, h of omega is the kinetic energy, which is omega dot minus Laplacian inverse on omega. And the Casimir is the helicity, which is omega dot curl inverse omega. And now the modified equations take exactly the form you would think they would take. The omega dt is the curl of u cross the new omega twiddle, the anticipated 3D vorticity. Okay, so this is what I said earlier. I don't have to say much about this. We had the only Casimir we have for 3D Euler is the helicity, and the helicity is usually kind of discounted because it's not sign definite. But this works if you take the square of the helicity also, and then you can apply the same theory. Okay, so here are some examples, and then we'll talk about conclusions. So this is an example that I hope is close to your heart. So we're going to modify the Euler-Boussinesq equations in 3D to make the anticipated version. So we write the Hamiltonian in terms of the total vorticity and an operator curl inverse on it, where curl of R is the Coriolis parameter. We take the variational derivatives now with respect to Q and with respect to B. B is the buoyancy in the Euler-Boussinesq equations. Okay, then since B is dragged and the potential vorticity is also dragged in this theory before it's any kind of modification, we have a whole family of Casimirs. So we have all functions phi integrated as functions of Q and B, and Q, as we know, is Q dot gradient of the scalar buoyancy. Okay, so we can choose the entropy if we wish from this group, and take what we need in this formula, the curl of dc dq. It's the curl of Q dot grad B, and dc dB is minus that divergence, and then the dissipative Casimir Euler-Boussinesq equation is the same one that we know, except now we're changing the total vorticity. We're modifying it. And this is the modification, and that L is the scale awareness factor that can change how important this is at different scales. All right. So it's pretty easy. Right? Once you have this structure, you can take whatever theory you like and put it through this structure, and it'll come up with a set of equations which is of the same form you had before, but now modified by the anticipated term. Okay, so for the fluids, now we come to the circulation theorem. We could look at the motion equation also. Take this curl off and add the gradient on the other side. And this is the usual, well, when theta equals 0, then we get back to the usual equation. This is an additional term compared to the usual form for the Boussinesq equations. And with this term, the entropy decays, but the circulation, okay, has an additional feature. It has the part where gradients of buoyancy that are not vertical generate circulation, but so does this other thing. Okay, and this is a spurious generation of circulation from the viewpoint of comparing with the original problem. But if you put in viscosity here, it would also appear there, and the viscous term would also generate circulation. Okay, so this is like I said, some kind of nonlinear viscosity, and what it does is it creates circulation of the integral of the velocity in the frame, in the rotating frame, the total velocity. Okay, so here's the summary. So the 2D anticipated vorticity equations can be written this way with a modified omega. The 3D Euler equations with anticipated vorticity take this form. And the 3D modified anticipated vorticity Euler-Boussinesq equations take this form. And in each case, the theory here gives you the modification to the quantity which is being transported. Okay, and you see what's happening is the time derivative of Q depends on gradients of this Q twiddle. So, and if you put Q back in, right, the total vorticity, then you'll get back your circulation theorem, and you'll get back point vortices and sweeping vorticity by the flow. But if you have that term, then you won't.
So
yeah.
You have a whole range of Casimir functions here. You've chosen one.
Oh, yeah.
What happens if you choose another one?
Okay. You just put it into that slot, dc d omega.
Yes, but would
right.
the equilibria depend on that?
Oh, the equilibria. That's a good question. I think so. Yeah, I think. See, the equilibrium comes in here, right? Okay. So let's see. What is the equilibrium condition? The equilibrium condition involves. So we put this to 0. Okay. This cross product has to vanish, and that curl has to vanish, and that curl depends on the CD Q. Yeah. So yeah, it shifts. That one is. I didn't think about that. I was thinking about entropy, but that might be something that forces you into your choice. That you have to choose this quadratic object. You have to choose the object that will not give you spurious equilibria.
So we're missing curl on this slide for the 3D Euler equation case.
This one here?
Yeah.
Yeah, that's the curl.
In the definition of the modified vorticity.
Here.
Yeah, should there be a curl?
Yeah, that's right. There should be a curl here. Right, thank you. Yeah. Okay. So other examples follow the same pattern. And I think what I'll do is, to allow questions, I'll sort of skip over the shallow water example and talk about conclusions. Okay, so we introduced this theory of selective decay by Casimir dissipation. Okay, and it suggests that we might use it as a framework for designing anticipated vorticity type numerical methods, if we wanted to do that. And the framework actually fits into the history of this subject pretty well. In particular, Rick Salmon has been using this triple product Nambu form and trying to design simulation algorithms for grid structures. So following his direction might be useful here. And I think the applicability, one of the features is, I mean, you know, like the Jupiter's red spot changes very slowly. But, you know, the action of vorticity in a problem is very slow, and maybe if we're doing this numerically, we'd like to have a model that, you know, that gives us a more realistic timescale to see how things go to equilibrium. So this might be a possibility. I think those timescales are going to be much less than the timescale for just viscous decay. I hope that the Voronoi methods that are being used and developed for anticipated vorticity in 2D could be adaptable to 3D, these selective decay models. And I hope this, you know, and that's one of the things that I'm interested in, working with people interested in modeling multiscale interactions during this program. And I'm hoping that this might be one of the avenues for pursuing this idea. Okay, and so the future applications of this approach would, you'd imagine parameterizing these interactions between disparate scales. And a paper which starts off in that direction, it's not exactly consistent with what we're talking about here, but it's close in spirit. It's this paper by Marshall and Adcroft in 2010. There are various analytical questions about whether the selective decay equations admit existence. Okay, and I suspect that they probably do, because they're decaying higher norms. If you go the other way and keep the entropy and decay the energy, because you're not decaying the strongest norm, it's possible that you won't be able to prove anything about existence. Now, so the open question is, should we pursue this as a turbulence model? And I don't have an answer for this. Because on the first, we've introduced a new torque, or a new force in this problem, this constraint force. So the equations don't conserve momentum, they have no stress tensor, and they don't conserve circulation. However, people who use this method for the 2D inverse cascade actually say that it models it pretty well. So it may be we don't need all those things that people usually put into, say, an LES model to just try this. It'll be something, well, it'll be its own type of model. And a question which is open is that, does this Casimir dissipation approach actually give you saturation of the nonlinearity or the decay to the equilibria, or select equilibria for you? Can you prove that? Okay, so I don't know how to prove that right now. And finally, the VCY 1989, the Vallis et al. Paper, does all these things. It does, you do prove that selective decay takes you to equilibria, and the VCY 1989 also has a Kelvin circulation theorem, and it fits also into this mathematical theory just by switching two things. So you switch the H and C, and you switch a commutator that's appearing in the metric or dissipated bracket into the L2 dual of a commutator of vector fields. and then it goes straight through and you get BCY and the various generalizations of BCY also for all the various other fluid theories too. Okay, so any questions? Yes.
Could you help me understand what theta is and how you would choose it?
Could you speak up? I didn't quite hear
Sorry,
you.
I was going to say, could you help me understand what theta is, what it means, and
What
how
theta
you,
means? Okay.
and how you would choose it?
Yeah. Well, in anticipated vorticity, theta is some constant times the time step. It's connected to the numerical method. I don't have a derivation of these equations from the original equations. What I'm doing is simply asking, could I make selective decay using the bits that are around and add one more bit? Right now theta is just a parameter, and
It controls the exponential decay rate of the.
that's
thing
true.
is-
That's right. It does. It has units of time. Yeah. So the rate is. Yeah. Okay. So it doesn't control the exponential decay factor, but that's that L2 norm. But it does, or the norm associated with the operator L, but it does control the units at which this thing decays. Okay, so you choose theta to be so many units. And I was only just following what is done in anticipated vorticity. You know, a lot of people have thought about this theta and written about it. I think that the consensus is that it's a time scale.
So I thought about it a bit more, and exactly, it doesn't. There's no Kelvin circulation theorem, but the integral of the right-hand side is 0. It doesn't globally create vorticity, because
We should talk offline about that. Okay.
because I don't. You can't conserve entropy and
We're not
have a Kelvin
conserving.
circulation.
We're not conserving entropy.
Yeah, vorticity is still locally conserved.
Yes.
So you can write it in a flux form, but it doesn't have the circulation. conserved anymore.
Exactly, and that's how it destroys entropy, is by fluxing across material.
Yeah, I want to not talk about this in a high level. I want to talk about this in details. Okay. Mark.
What's the question over there?
Just a comment really, I mean, with all of these things, it becomes a physics choice, not a mathematics choice as to what you do.
Yes.
So it's
Yeah.
it's going to be different for 2D flow versus 3D flow. I mean, the BCY might work for 3D, but anticipated vorticity might work much better for 2D. And furthermore,
Right.
you might in fact, pursuant to Todd's comment, not want to conserve Kelvin circulation theorem because the turbulence might be doing something to it for the resolved flow. So it's not a priori good to have a Kelvin circulation theorem for the resolved flow.
It's right, but in terms of interpreting the solution, it's a priori good.
Well,
Because
well,
then
mathematician
you
might
can
be.
have like point vortices being swept around vortex filaments. And the difference is that the transport velocity changes, but you still have the same structure if you have this Kelvin circulation theorem. But if you're putting a constraint in that introduces a constraint force into the problem, you no longer conserve momentum and you don't conserve. Well, you have a way of creating the circulation that you use that the unmodified model does conserve. More? Okay.
Great, thank you very much.
Thank you.